The next speaker is Christian Bertoni, and he will talk about minimizing couplings in renormalization by preserving short-range mutual information. Please.
Yes. Okay. Thank you. Hello. Yes, I will be presenting this work about some aspects of how could one use some information theoretic methods to inform some renormalization method in statistical mechanics in its joint work with Joe Renes. And okay, yes, this talk will be maybe a little different from the others in this conference. It will be primarily about renormalization in classical statistical mechanics. So I will be talking about classical statistical mechanics models on a lattice, and in this context, renormalization is a process which progressively removes degrees of freedom from the system in order to get an effective model at larger scale. So the typical textbook example is block spin renormalization, where you take your lattice and you cut it up into blocks, and you apply a map to each block that maps your block to, let's say, a single spin. And what you obtain is a system that is, in some sense, zoomed out. You look at it from a larger scale, and you forget about microscopic details, and you only look at the macroscopic picture. Very briefly, why do we do this? Because it's useful to study phase transitions. We know that critical system at phase boundaries flows towards some fixed points, and away from the criticality, the system will flow towards other unstable fixed points. And there are universal phase properties that can be extracted from the flow, for example, critical exponents. But in defining this map, I've been kind of vague. You take your block and you map it to a single spin. There are several ways one could imagine doing this. And in fact, not all possible maps that you could choose are equivalent in some way. For example, if one thinks of the prototypical example, the 2D Ising model, or any other two-level system, one might imagine, well, let's do something called decimation. Let's take as our renormalized spin the top left spin in our block always. So this essentially amounts to tracing away 3 spins every 4 in our probability distribution. Well, intuitively, one might argue that this is a good idea because in my larger scale effective model, I only care about, let's say, the correlation between this spin and this spin, and not correlation between spins that are close to each other. But one could equivalently come up with other examples. For example, the famous majority vote. These are all very famous textbook examples. I'm sure you all have seen. But if the majority of spins in my block are spin up, then I pick spin up in my renormalized system, and vice versa. And one could argue that here the philosophy is also kind of respected, because we are, in a sense, summarizing what is going on in the block in a single spin. We intuitively only need a map such that in a sense, the important information about the probability distribution in this block is summarized in the single spin that is our renormalized spin. And here we need a way to break ties in a 2x2 block, since there will be ties. And in this case, we could choose, for example, to break it at random. So if there are 2 ups and 2 downs, we just flip a coin and pick this way. But the point is just that there are several examples that one might come up with, which are equally, let's say, intuitive, and that should intuitively work as a renormalization map. But it is known that, for example, for the 2D Ising model, majority vote numerically works much better than decimation in extracting critical exponents. And there is no clear reason why in general. For example, for the 2D Ising model in particular, you could come up with justifications such that majority vote better preserves the magnetization. But for more complicated models, it shouldn't be so clear, right? And so you see where I'm getting at. We could ask the question, is there a general criterion to choose an optimal, in some sense of optimal, renormalization map given some model, the renormalization map that should give you the best results? And in 2018, Maciej Koch-Janost and Zohar Ningel came up with this RSMI algorithm just to answer this question. RSMI stands for Real Space Mutual Information, and their proposition is that, well, what renormalization is supposed to do is it is supposed to give you an effective model that works at large scale. So what you are interested in is that you preserve whatever information the block has about its faraway environment. You don't really care about short range stuff that goes on between the block and its immediate surroundings. You care about the information that the block carries about its faraway environment. And so you take your block A, which you have to renormalize, its immediate boundary B and faraway environment C, and you look for the map that best preserves the mutual information between the block A and the block C. So you see this mutual information between A and C must decrease under this map R due to the data processing inequality. And so we look for the map that for which this drop in mutual information is the lowest. And the rationale is that this preserves as much long-range information as possible and should discard a short-range one. And this optimization in the paper is done by parameterizing a subset of all stochastic maps and using machine learning to optimize these parameters to find the optimal map in this subset. And it does deliver good results. It recovers the majority vote map for the 2D Ising model, and it also gives good results for more complicated models. But one might ask, what is a more practical reason why this works beyond the intuitive reasoning that this preserves long-range correlations? Is there a more practical way to see why this works? And a proposed, at least partial justification for why this works was given in another paper by Patrick Langenhager and co-authors, where among other results, they show that probably at least a partial reason why RSMI works is that it minimizes the proliferation of couplings in the renormalized Hamiltonian. So a typical problem affecting renormalization maps is that here now we transition quickly to 1D. You have your block and you apply the renormalization map to your block and you have a new probability distribution and you look for the Hamiltonian that describes the probability distribution. And you might not have a nearest neighbor model anymore. There can and will appear longer range couplings all over the place. And this will be difficult to treat and will ruin your renormalization scheme. And they argue that if this mutual information that RSMI optimizes is actually exactly preserved, then there can be no long-range coupling appearing between the two faraway portions of the environment, C1 and C2. And so the question that we try to ask ourselves is there a systematic way to examine this relation? What is the relation between preserving these kinds of long or short range information in the lattice and eliminating long range couplings in the renormalized Hamiltonian? And so we come to the results that we found. In 1D and these are results are valid primarily in 1D, but also in isotropic d-dimensional systems for NED. We find that actually there is no block spin renormalization map that can create any couplings between A and C, so the block and its faraway environment, or even between C1 and C2. These are just never coupled in by a single block renormalization map. And we actually find so that the only non-trivial couplings that could appear are between B1 and B2, so between the two disconnected parts of the boundary in 1D. And that to minimize these kind of couplings, we actually have to intuitively optimize the preservation of mutual information between the block and its boundary, so between A and B, which kind of goes against the whole philosophy, but I'm gonna talk about this a bit later. Another interesting thing we find is that the optimizers for both problems must be deterministic maps. So by both problems here, I mean preserving as much long-range information as you can and as much short-range information as you can. Both problems must have a deterministic optimum, which could be useful, I think, to inform the machine learning algorithm of the RSMI algorithm. And finally, we find actually after the short-range information after renormalization is lower bounded by the long range information after renormalization. So this means this actually means, in a sense, that the RSMI optimization is a sort of relaxation of this short-range optimization, and that by optimizing as much as you can the preservation of long-range information, you're actually, to some extent, asking to preserve also short-range mutual information. And here I want to make something clear. Here we are not like proposing a new algorithm or suggesting that actually optimizing the preservation of short-range information should give better like actual renormalization results for the standard measures of the quality of a renormalization map, because as I said, it kind of goes against the philosophy to keep as much short-range information as you can. But this kind of shows a sort of missing trade-off that you would expect between keeping long-range information and keeping short-range information. This shows that, in a sense, the optimization that RSMI does would not be equivalent to throwing away as much short-range information as you can. But there is a non-intuitive trade-off between these two, that to keep long-range information, you also have to keep, to some extent, the short-range one, and also you have to keep the short-range one to get a manageable renormalized Hamiltonian without long-range couplings all over the place. And so I will briefly describe the methods that we used and a bit the results a bit more in detail. The chief technique that we use is a very well-known result in statistics called the Hammerstein-Clifford theorem. And it states that the probability distribution on a graph is the Gibbs state of a local Hamiltonian if and only if it is a Markov network. So by local Hamiltonian here, I simply mean a Hamiltonian that can be decomposed as a sum over the cliques of the lattice, where the cliques are essentially nearest neighbors pairs. And by Markov networks, a Markov network is, I'm sure everybody here knows, but is a probability distribution on a graph where every two faraway spins, the correlation between any two faraway spins must be mediated by the spins that are in between. So if we divide up our lattice into some region A and it's bound, and sorry, into three regions A, B, and C, such that every path from A to C must pass through B, then we must have that A and C are mutually independent. So the conditional mutual information between A and C conditioned on B must be zero. And so already here we see, for example, one might have asked in the RSMI algorithm, why mutual information? And it's not some other information theoretic quantity that relates the correlation of various parts of the lattice. Well, if we want to connect this to couplings in the Hamiltonian, we see that, well, this is very intimately related. There is a very intimate relation between mutual information and the locality of the Hamiltonian, if we want. And so our main results kind of fall out of this pretty quickly, is that the first result is that there will never be any couplings introduced between the central renormalized block and the faraway environment, so A and C, and this is a simple consequence of the data processing inequality. So we start from a Gibbs state, so this must be zero initially, and we apply our map to the block, and since it was zero initially, it can only decrease, but it must be positive due to the strong subadditivity, so it still must be zero. And since this mutual information is zero, it means that if you build a graph, if you take the new Hamiltonian and you build a graph by connecting via an edge all of the spins that are coupled in the Hamiltonian, then there are no paths that lead directly from A prime to C. So A prime and C are not coupled in the renormalized Hamiltonian. And a similar argument leads us to say that there can never be any couplings between the two disconnected faraway parts of the environment, simply because this mutual information between the two C1 and C2 condition on the boundary is zero in the beginning, and this is just not affected by the renormalization map. So even if data processing inequality does not apply to the conditioning system, we don't need it here. And then, so this means that the only non-trivial couplings that we can get are between the various parts of the boundary, and we show that this conditional mutual information between the two parts of the boundary conditioned on the central block after renormalization is bounded by the difference in mutual informations between the block and the boundary before and after renormalization. And well, we can argue that obviously if this is zero, this is also zero. So if the left-hand side is zero, there are no couplings. And if the left-hand side is small, then the probability distribution is close in total variation distance to a distribution where this mutual information is 0. And so the couplings are weak between the two disconnected parts of the boundary. And these results can also be extended to higher dimension just by in an isotropic system just by repeating the 1D argument by looking at this multidimensional system as a series of 1D stripes. You just show, for example, that there are no couplings between here and here. If you pick a certain optimal map, then you turn the system on itself and you do the same optimization here. And since this system is isotropic, you will find the same optimum here as you found here. And so this result just translates to higher dimension in isotropic systems pretty naturally. And finally, we show that the optimizer for both of these must be a deterministic map. And we simply show that if we, for a fixed probability, bipartite probability distribution of two systems A, B, if we take the map from some map R to the mutual information when we apply the map to one of the two systems, as seen as a, I'm going to say the word map a lot here, as seen as a map between the stochastic maps and the positive real number, then this is convex. This is a convex map. And by standard convex optimization, we can argue that since the stochastic maps are the convex fold of deterministic maps, then both of these must be deterministic. And this has some implication, for example, for both for the Rsmi algorithm and for our proposed short range optimization. The random tie break majority rule map cannot be optimal simply because it is not deterministic. And quickly at the end here, we have a numerical example in just the 2D Ising model. We can consider the 2D Ising model and 2x2 blocks, and we can simulate this using tensor networks and the convex transfer matrix method. And we pick a bunch of maps to choose from. So we can use decimation, the one I described at the beginning. So we just pick always the top left spin to do our optimization, to choose a renormalized spin, or we have majority vote. So if the majority of spins in the system are up, we pick up as a renormalized spin. But then there are ties, and these must be broken. And we can do this in 4 different ways. Either we choose a fixed value. So for example, we decide that the tie is always broken with +1. If it's even, then we put +1 always, or -1. This is a different map. We can do it at random. As we said, this cannot be optimal. Or we can do a hybrid between majority vote and decimation. So we, if there is a tie, we pick one spin in the block to be the renormalized spin. Or there is this last kind of, let's say, a bit stupid map, bias map, where every configuration is simply mapped to +1, except for the -1, -1, -1, -1 configuration, which is mapped to -1, or vice versa, two versions of this map. Just to say that also you can pick maps that obviously should not work for the common sense renormalization picture. This would make absolutely no sense, but we want to see whether there is an information theoretic way to exclude them in some sense, whether they make sense from the RSMI or our point of view. And so since we know that the optimum is a deterministic map, we can just, and we have 2x2 blocks, we can just simulate the probability distribution and brute force check all 2 to the 16 maps. And we find that one of the maps that I described previously is always optimal at some point in the temperature range that we examined. And plus we added in random tie break majority vote since it's so common for the 2D Ising model as a textbook example. So we find that at very low temperature, below the critical temperature, this weird biased map is actually optimal for these purposes. But this is not so surprising because what we actually have is that at very low temperature, our system is essentially a symmetry broken state with either or plus or all minus. And by taking all configurations that are all plus and that are in all minus, and mapping them to all plus, we are basically asking the system to flow towards the 0 temperature fixed point. And a bit more interesting stuff happens as we go a bit higher in temperature and we approach the critical point, and there is a very sharp transition just a bit above the critical point, curiously enough, where this fixed map becomes really bad, as it should be, and is replaced by one of the two tiebreaker version of majority votes. And for a little bit, this is the optimum. And then at the critical temperature, the other fixed version of majority vote joins it and becomes the optimum as well. And this is easily explained before. Here, the notation we've used is, for example, the fixed majority vote. You can choose to break the ties with up or break the ties with down. And this means that the tiebreaker spin that we choose is aligned with the symmetry broken state that the state chooses in the simulation. And so it's obvious that the aligned version should perform better than the unaligned version. But above the critical temperature, this difference is erased because there is no more symmetry broken state. And so we find that the majority votes are optimal for a while until at very high temperature, the majority vote with this decimation tiebreaker becomes optimal. And finally, at very, very high temperature, decimation itself becomes optimal. But what we can notice around the critical temperature, and here maybe I should point out that this is the difference between the loss of mutual information of the map that we are considering and the loss of mutual information between the optimal map. So none of these maps actually exactly preserve mutual information, which would be really unexpected since this would imply perfect recoverability. Around the critical temperature, we find that first of all, decimation performs terribly and majority vote performs way better. It is some versions of majority vote are in fact optimal as expected and as the Rsmi algorithm finds. And we also find, as expected, that random tiebreak majority vote is never optimal because it's not deterministic, and it also performs, but it still performs better than decimation, but it still performs significantly worse than the other kinds in this, at least in this interpretation. And yes, this is what we can say around the critical temperature. So just a couple of points to conclude. We found that, in a sense, this relationship between these heuristics of preserving long-range information, which is not as trivial as it looks. There is a non-trivial relation between preserving long-range information in the lattice and preserving short-range information in the lattice. Preserving the short-range one does not imply throwing away the short-range one. And also, you need, to some extent, to preserve the short-range couplings, short-range mutual information in a renormalization map to get a tractable Hamiltonian out of it. And we also found that the optimizer in the Rsmi algorithm should be looked for among the deterministic maps. So this could inform the machine learning method that they're using, because it greatly obviously it greatly restricts the search space from all of the possible stochastics map to a finite set of very large but finite set of deterministic maps. And then there are some questions. We might ask, okay, but if we actually do this optimization numerically, is the map that we get out of it a good renormalization map in any sense? The Rsmi algorithm with its, let's say, heuristics finds actually a good renormalization map, but it is not at all obvious that by using our optimization, we actually do find a useful renormalization map. The intuitive answer would be probably not, because well, as I said, it kind of goes against the whole philosophy of preserving long-range physics and throwing away short-range physics, but this still might be interesting. And if we actually do the Rsmi optimization, what actually, we know that to some extent, this accidentally, in a sense, implies preserving also short-range couplings. And how much and what sort of short-range information does this map preserve? And finally, it might also be that these two problems are kind of the same problem in disguise. We found with the example of the 2D Ising model that essentially the optimum that we find is kind of the same. We both find majority vote, even though we searched the whole space of deterministic maps and we found that majority vote should be the optimum. But the Ising model is kind of a very simple example. Are there interesting examples where the two optimizations yield different maps? This is also a possible future question to investigate, to really see whether this isn't actually the same or a very similar thing in disguise. So yes, I think my time is up. And this is all I wanted to say. Thank you.
Thanks a lot, Christian. A nice talk. We have plenty of time for some questions. Okay, let me then ask the obvious one. Can you do this for quantum states? I can imagine that for commuting Hamiltonians, at least, maybe some of the proof techniques would hold.
Yes, exactly. This is a question I expected. You're right that the obvious question is, can we do this for quantum? And this was also the initial question, right? Like, can we do this can we do something similar to RSMI, but and justify it for quantum systems? The problem with applying these results is that I talked about the Hammerstein-Clifford theorem, and this is a double, and it's very important that this is a double implication. And this is a double implication only for classical systems or commuting Hamiltonians. So for commuting Hamiltonians, basically everything translates. But for non-commuting Hamiltonians, which, well, I mean, are actually quantum in a sense, there might be something to do, and some approximate versions of Hammerstein-Clifford hold, like in the previous talk, Antonio Perez was mentioning this mutual information decreases exponentially with distance, but it's not zero. So you cannot just straightforwardly apply Markov networks techniques. You have to go to approximate Markov chains, and it becomes more complicated. So it probably can be extended, but it's not obvious.
Okay, say at high enough temperature, maybe you can get some approximation, but not for all.
Yes, exactly. But then you're interested in the critical behavior, right? The behavior around the critical temperature. So this might not be practical.
That's right. Okay. We still have some time for more questions. Cannot see anything on the chat so far.
And I have said this is a quite different topic for the usual that is dealt with at this conference, I guess.
Well, I think we're having more and more mini-body systems talks, so it's I think it fits very well the audience actually. But then if there's no more questions, then I guess if there are any again, we can just ask them in the Slack channel.